sublevels. Normally, electrons occupy the ground state, which, as we know, is the lowest energy level available. How do you know if the electrons are in the ground state? If the electron configuration given matches the periodic table. So, for example, if I tell you that oxygen with a configuration of 2-6, if you actually go to the periodic table and look up that shell configuration, it matches the periodic table, which means that this configuration is said to be in the ground state. The excited state, remember, this is when electrons that are in a higher energy level than they were originally. How do you know electrons are in the excited state? If the electron configuration does not match the periodic table. So if I gave you the configuration for oxygen to be 1-7, right, you know that this is oxygen because it has 8 total electrons. So we know it's oxygen, but we know that according to the periodic table, oxygen is 2-6, so it does not match. Does not match, and therefore it is said to be in the excited state. So what if you are given the expanded configuration? You know, the 1s2, 2s2, 2p4. If you're given that, right, how do you know if that's ground state or excited state? Excuse me. If one sublevel doesn't fill before the next one starts, or the sublevel or orbitals fill out of the normal order, right? So for example, if you saw 1s2, 2s1, 2p5, we know that this is oxygen because 5 plus 1 plus 2, it's still 8 electrons, right? Just like up here, 4 plus 2 plus 2, that's 8 electrons. We know that those are both oxygen, but the fact is that the 2s did not fill before electrons were put into the 2p. Therefore, this is said to be excited, right? So if they filled out of order, then that's a pretty good indication that that atom is said to be in the excited state. The next question that you're going to be tasked with determining is whether or not a certain level is occupied or full. And when we say occupied or full, we're referring to are electrons occupying the sublevel? Are electrons full up in that particular area? Okay. So we say it's occupied if there's at least one electron present. And if it's full, are we talking about, is the principal energy level full? Is the sublevel full, or is the orbital full? And if they're filled to capacity, then we can indeed say that it's full. If there's at least one electron present, but not necessarily full, we would refer to that as being that area is occupied. So we got to look at principal energy levels separate from sublevels, separate from orbitals to be able to answer these questions. So if the question is regarding principal energy levels, it's helpful to know that the first principal energy level has a maximum of 2 electrons. The second principal energy level has a maximum of 8. The third has a maximum of 18, and the fourth has a maximum of 32. Consult a blank orbital diagram. I can't even spell. If you consult your blank orbital diagram, you will be able to see where I'm getting those numbers from. Okay, but we're working with these numbers knowing that that's the max that any principal energy level can have. And so we're going to continue to look at oxygen as our example, right? We know that it's 2-6. And so the question is, first, how many principal energy levels are occupied? Well, the fact that there's 2 numbers here means that there's 2 principal energy levels occupied. Are they full? Are those principal energy levels full? That's the second question. Well, since the first principal energy level can hold 2 electrons, we see that that principal energy level is full. The second principal energy level can hold 8. We don't have 8 in the second principal energy level, so that second principal energy level is not full. So we only have 1 principal energy level that is full, and that's the first energy level. Okay, so to look at the principal energy levels, you must consult the shell diagram on the periodic table. That's going to be your best bet for figuring that out. For sublevels, the The S sublevel can hold a maximum of 2 electrons. The P sublevel can hold a maximum of 6. Remember, the P sublevel has 3 boxes. The S sublevel has 1. The D sublevel has 5. And the F sublevel has 7. Okay, and each one of those boxes, each one of those orbitals can hold 2 electrons. So the D can hold 10, the F can hold 14. So now the question is, how many sublevels? Still we're working with oxygen, the 2-6. You can't really tell just by looking at the shell diagram how many sublevels are occupied or full. So what you're going to need to do is write out the full configuration to answer. So 2-6, this 2 are the 2 electrons in the 1s. The 6, those 6 electrons are spread out over the 2s. There's 2 in the 2s. And their remaining 4 are in the 2p. So if we are looking at the full electron configuration, we can now decide how many sublevels are occupied and how many are full. So to answer how many are occupied, well, 1, 2, 3. I see 3 sublevels here. There's 3 sublevels occupied. Is each sublevel full? The 1s sublevel has 2 electrons. The 2s sublevel has 2 electrons. The 2p sublevel only has 4 electrons, so it is not full. So we therefore have 2 sublevels that are full. So to answer the question about sublevels, whether they're occupied or full, you have to write out the full configuration. Orbitals, boxes. Any single orbital or box can hold 2 electrons max. So what you're going to need to do to answer the question how many orbitals are occupied or how many are full, you're going to need to write out a full orbital diagram. So if we do that, it's going to look like this. So we have 1, 2, 3, 4, 5 orbitals that are occupied, and we have 1, 2, 3 orbitals that are full. I'm out of time. See you in the class.